Hello, welcome. Today let's try to solve some Leetcode problems. So I'm gonna try to solve the 10 Leetcode easy problems. So from problem 104 to problem 136. Now let's try to solve the first problem. So this problem is about to solve the maximum depth of binary tree. So we're just giving a binary tree. We need to return the maximum depth. So this depth is just the first node. This is layer 1, layer 2, and layer 3. So that is why return 3, not 2. Yeah. So it is always dependent on how many nodes at one pass. Yeah. Now, let me try to solve this one. So the easiest way to solve this problem would be the DFS. So, yeah, I think I can use a DFS or check it directly. Yeah, let's do it directly. If not root, if not root, so I can return 0. Otherwise, I can return max of the two side. So maximum of depth from root dot left and it's right. And I need to plus 1. So let me check for this one. Yeah, so if I'm going to check this one, so the root is 20 and its left side is 15 and the right side is 7 because this is easier. Yeah, just to check this one. So I'm going to check from the left side. So if not root, so I have root. And then I will check the maximum self dot left, go to its left side, it's here. Yeah. Now I will still go to the DFS. So left and right it is a 0 and this is 1 and this is a 1. So plus 1, the result is 2. So it means it should be right because this is 2, this is a 1, the maximum is still 2 and plus this one it should be 3. Now let me run it. As you can see, it works. Yeah, now let's continue to solve the next. So this one would be convert sorted array to binary search tree. So there will be, there is also a medium Leetcode problem. It's exactly the same. Yeah, it's gonna still be the DFS. So for this problem, we are just giving a sorted array. We just need to return the binary search tree, but it should be heap balanced. So the heap balanced is actually a balanced binary search tree. Yeah. So we're gonna use the DFS. So let me define the DFS function. So I will prepare a left and right index because this is gonna be easier to check which numbers is at the left side and which numbers should be at the right side. And then I'm gonna solve the big problem into the sub problem, to the small problem. And then it's gonna be smaller and smaller until I get the result. So I need to check if this L index is more than R. I need to return a none because finally I need to return a binary search tree. Yeah, let me return the DFS first. So the DFS would be starting from 0 and the right side should be length of nums minus 1. So for here, if it is not, so I can get the midpoint. It should be L plus R minus L and divided by 2. Yeah, because this M must exist. Yeah, because here, this L is more than R. Otherwise, it is less than or equal. So this m must exist, I can have a root. So the root should be equal to the tree node with this nums m. Now I can prepare the root dot left and the root dot right. So root dot left would be the DFS. So from the L to m minus 1. Yeah, because this m is the root. Its left side is L to m minus 1. And similarly, I can copy to the right side. So the right side would be m plus 1 to r. And finally, I need to return the root. Yeah, so let's just have a check. So for this one, if this L equals to R, so M just have one value. So if this R equals to L, so it's gonna be 0 and M should equal to L. And here I got a root, and its left side, this L should be bigger than this M minus 1 because L equal to M. So I'm gonna return a 0 at its left side, and its right side is the same. M plus 1 should be bigger than this R. This R. Now let me just run it. It works. Let's submit. Yeah, so for this problem, we are just giving an array. Because the array is sorted, as you can see, it works. We can just split it into two halves. So this is the left side, and this is the right side, and 0 is the root. And then we're gonna solve the subproblem. So for the subproblem, we need to check the return conditions. So in which condition it should return. So this is what we need to check. Now let's continue to solve the next balanced boundary tree. So for this problem, and there are basically, I think, two ways. Yeah, the easy way and the hard way. So the easy way is just like solving the depth of boundary search tree, but it will be O(n) squared because for each of the nodes you need to check the depth of the left and the depth of the right, and then for this node you should still do that. As you can see, it's gonna be O(n) squared. Yeah, but there's actually a better way to solve this problem. It's gonna be O(n). So that is the post-order traversal. So for the post-order traversal, you will always check the left first and then the right. If you find a case that is not hit balanced, you're gonna return a false immediately. You don't need even to go to this route if you find a false. Yeah, so here are two examples. Yeah, but for these examples, you should always check to this route, but it's not a good example. But if at the left side there are still more nodes, but at the right side there's no nodes, you don't even need to check this node, because at somewhere while you find a false, you're gonna return a false immediately. You don't need to go to this route. Even you go to this route, it is just O(n) time. Yeah, so that is why the post-order traversal is better. So let's define a DFS function. So this DFS is just the post-order traversal. I'm gonna prepare a node. So I need to check if the node exists. So if not node, I'm gonna return a 0. Then I'm gonna prepare a left should be equal to DFS. It's the left side. So for this left, I need to have a stencil check. Yeah, at the moment I will not give it. Let me give a -1 first. You can also give -2. It's the same. Yeah, and later on I will explain why it should be -1. So the right should also be the same because it is a post-order traversal. You need to get the left and right first before you go to the node. Then we can also check the right. if right equal to -1, or the absolute of left and right. Yeah, left minus right. If the absolute of left minus right is more than 1, we are sure we're gonna return a -1. So why we return a -1? Because we want to let the -1 represent it is a false condition. Yeah. So finally, if we didn't return -1, it means everything is okay. So we needed to return the depth. It should be the left and right, maximum of left and right plus 1. Yeah. So finally, we just needed to return this DFS should not equal to -1. If it is not equal to -1, it means it is not false. It must be true. So why you can find the left is -1? Because here is a condition. According to this condition, no matter it goes to the left side or its right side, if we find a left minus right, the absolute is more than 1, we would always return a -1. So this is why we can find a left equal to -1 and right equal to -1. If we find either of that, so we can return a -1 finally. We don't need even to go to the node. Yeah, we can just check the left side and the right side until we find a false. We don't even need to go to the root. Yeah, even we go to the root, it is still ON because it is not like the depth of a binary search tree. We have to check, for example, this node, we have to check all of them. And for this one, we have to check all of them. Yeah. Now let me run it. Yeah, it works. Now let's go to the next. So this is the minimum of a binary search tree. And yeah, for this problem, this is a little bit different from the maximum of a binary search tree. So I think the easiest way is BFS. So instead of the DFS, I think BFS is easier to understand. Yeah, so why it can be solved by BFS? Because yeah, it's just we are giving a tree. According to this BFS, we can find if this node is the leaf. How can we check if this is the leaf? We can just check if there's no node at the left side and there's no node at its right side. It means this is a leaf node. If it is a leaf node, we should know. We should know the depth of this one, because for BFS, we would always find the minimum first. We would always find this one first. So it's gonna return a 2. Yeah, because this is 1, this is 2. Yeah. Now let's try to solve it. So if not root, yeah, because even the root not exist, so we can return 0 because the number of nodes can be 0. Now we are sure the root must exist, so we can put it inside the queue. Inside the double-added queue, we can put we can put the root inside. Now we can just use the BFS. If there's some node inside the queue, so we're gonna pop it out. So this node should be equal to q dot pop left. But inside, we want to check the depth because this is 1, this is 2. We need also to put a value inside. Yeah. So instead of just a root, we can put a root at 1 because the depth for this root is just 1 at the moment. When it goes to this node 9, it's gonna be 2. So we're gonna have a node and depth. So gonna pop out from this queue. So we can have a check if not dot left and not dot right. Yeah, it means, for example, for this node, it doesn't have left and right. We can return the depth immediately. So otherwise, we're gonna check if not dot left. So we can put it inside. Yeah. So q dot append inside it should be the not dot left and a depth. So the depth would be the depth plus 1. And similarly, we can check from the right side. If not dot right, so q dot append not dot right and also depth plus 1. So as you can see, the BFS should be easier. Now let me, oh, I didn't return anything. Yeah, here is some typo. Yeah, I needed to, I already returned the depth from here. Yeah, now let me just run it. Yeah, as you can see, it works. Now let me submit it. Yeah, up to now, we are always solving the tree problems. Basically, they are the tree traversal problems. Now let's continue to solve the next. So this one is the path sum. There are a lot of problems, similar problems like the path sum. Yeah, as you can see, there are so many. Basically, they are the same solutions. Just yeah, by using the DFS. Exactly, it is a pre-order traversal. You just need to check the route and then go to the left and go to the right. Basically, you're gonna check all of them. So for example, this 5 goes to 4, so the total sum is 9, and then it is come to 11, it is 20, and then it goes to 20, goes to 2, it is 22. So if it is equal to 22, so we're gonna return a true immediately from here. Yeah, if we didn't find, if we go through all the paths, we didn't find this 22, so we're gonna return a false. Yeah, now let's try to solve it by using this example. So we can use DFS still. Inside it's gonna be a node. Here I will use a presum variable. So this presum will be starting from 0. So for this DFS, it's gonna be the root and yeah, 0. So if this presum plus sum equal to this target sum, it means I'm gonna return a true. If I didn't find, I'm gonna return a false. So let's try to check if we can solve it like this way. So yeah, if for the tree traversal problem, we shouldn't always check the node. Yeah, if the node not exist, we should always return something. And for this one, we need to calculate the sum of all the path values. And if not exist, so we're gonna return a 0. Yeah. So for example, if it goes to node 2, if it's the left side and the right side not exist, so we're gonna return. Yeah, let me check if the node not exist. If it's yeah, 0 is also a false. I think I can return a false as well. I will check it later. No, I believe the node already exists. I have to check if not dot left and not dot right, and yeah, if it's left and right not exist, it means this is a leaf node. If it is a leaf node, I can check if the pre-sum plus the current value equal to the target or not. So it should be not dot value equal to this target sum or not. Yeah. So if it is equal, I'm gonna return true. Otherwise, I'm gonna return false. Then I need to check its left side and the right side. It should be DFS not dot left. If I go to the left side, it will be pre-sum starting from 0 plus not dot value. If it is the right side, yeah, I will change it to the right. If it is the right side, yeah. So yeah. So for example, so for this node 5, it exists. I will not return false, and its left side and the right side still exist. Yeah. So it means it will go to the DFS, go to the not dot left. But while it go to the left, this pre-sum 0 should plus this value 5. Yeah. And similarly, while it goes to this 2, yeah, we're gonna let's check this 11 first. While it goes to this 11, we're gonna still go to the left and the right. Yeah, if it go to the right, so the pre-sum would be already be 20. 11 plus 4 plus 5, it would be 20. And not dot right should be this number 2. And then it go back to this DFS recursively. Yeah, and the not exist. If not left, it's the left side and the right side, its side do not exist. So we're gonna check if this 2 plus this 20 equals to the target. If it is equal, we're gonna return true. Yeah. So for here, it means we're gonna return the DFS left or right side. Yeah. It should be a return. Yeah, because it's not just a traversal. We need to return a value. And here is also a return. I think basically this is the entire code. I can set this to 0 as well, but I think, yeah, I can make a false directly, because if I return a false, it means while I goes to 2, I didn't find the value. And then I go to its child, I will return a false. There's something wrong. So the first one is wrong. Yeah, let me check it. Let me change this to 0. I don't believe so. Let me just, yeah, it should be false, not 0. Yeah, here I did some typo. It should be not. Yeah, if it's left side and the right side not exist, I gonna check it. Yeah, no, let me just run it. Yeah, as you can see, it works. Now let me submit it. Yeah, as you can see, it works. Now let's continue to solve the next. The next one would be the Pascal triangle. Yeah, this basically is a math problem. So we're gonna use some math tricks to solve it. Yeah. So let me just delete my code, existing code. Yeah. As we can see from the picture, so this triangle is just like that. It's easier to understand, just plus the values and just plus all the values, and this is just like a 5 layer because number of those is 5. Yeah, because the final result is just an array. So we can also prepare something for it. So I can prepare a result array, and inside I can put a value 1 because this is for the layer 1. Let's check how many number of those. Yeah, at least we have 1 rows. So basically, this is like a dynamic programming. Yeah, but there's still some tricks. We only need to use this one, use the last row. We don't need to check the others. So for example, if we want to calculate the last row, this n minus 1, we only need the row of n minus 2. We don't need to use others. So this is why we can prepare some data structure like a stack. So the result would be like this. And finally, we just need to return this result. Now let me just check from the second rows. So for I in range, from the second number of rows plus 1. So for example, if this number of rows is 2, if this number of rows is 1, so for example, 2 and 2, we will not do anything. We just need to return this result. If the number of those is 2, so this means we're gonna put append 1 though after the result. Yeah. So we can prepare this last row. Yeah, let me use the last row should be equal to the result minus 1. Now the last row should be updated with a padding 0 at the left and the right side. Yeah, because this is easy for the calculation. Yeah, if we pad a 0, it's gonna be easy for us to calculate this last row. Yeah. Now I will still use this last row. It would be equal to, yeah, let me put it inside last row I plus last row I plus 1 for I in range length of last row minus 1. Because here I use a plus, so here should be a minus, and then that is exactly the calculation. It is exactly like that. Now the result can append this last row. I think it's the entire code. Now let me just run it to check if it is like this. Yeah, as you can see, it works. Now let me submit it. So I will copy the code exactly like this, because for the next question, it's gonna be exactly the same. So here you can see it works. Yeah, now let's go to the Pascal triangle 2. Yeah, for the triangle 2, it's exactly the same. The only difference is we don't need to return all the rows. We just need to return the last row, this row index. And the index is just starting from 0. That is also different. And for our rows, for the last question, it is starting from 1. And this one, index is starting from 0. So we need to take care for the result. So here, it's gonna be a minus 1. And here, as the index just start from 0, so this means, yeah, we're gonna do change something. So for example, this one I'm gonna change to row index. So for here, yeah, if I just plus 1, it's gonna be wrong. So I have to plus a 2 because the row index just starting from 0. Now let me just run it. Yeah, as you can see, it works. Yeah, you can also change this one to 1, and here just plus 1. It's gonna be the same. So this may be, yeah, more meaningful to understand. So here this means the index is 0. Now you are going to start from index 1 to this row index. And finally, you need to return the row index. Now let me run it. And submit it. Yeah, now let's go to the next. So this one, the best time to buy and sell stock. Yeah, this is a good question because there are so many similar problems. We are giving a price. We need to calculate the maximum profit. So for me, I'm gonna prepare two variables, profit and lowest. So the profit would be starting from 0, and the lowest would be the first day. Now I'm going to start buying the stock and sell it. So for let me use a p for IP in enumerate the prices. So my current lowest value is gonna be the minimum of the lowest value with this p, and my profit would be the maximum of the profit with the current value p price, current price p minus the lowest price. Finally, I just need to return this profit. Now let me submit it. Yeah, now let's continue to solve the next. So next would be the valid palindrome. Yeah, we are giving a string. So this string just have lower and uppercase English letters, and it also has some other characters like the comma, empty string, and also the, I forget how to call it, semicolon. It is not called semicolon. Yeah, but it's different kind of characters. We just need to connect all those valid characters. If it is uppercase, we're gonna turn it to lowercase, and we're gonna check if it is a palindrome or not. Yeah, now let's just do it. So I'm gonna enumerate it from the string. Yeah, let me prepare a result. Just be an empty string. I think I don't even need to enumerate. I just check the characters inside. So for C in S, if C dot is L num, so this means if it is an alphabet and num, so this alphabet also include uppercase and lowercase English letters. It also includes the digital numbers. If this C is L num, what are we gonna do? So this result would plus this C. Yeah, now let me check this result. Should be equal to result it should be reverse. Yeah, so this is just a reverse. Yeah. Now let me print out the result. I'm not sure if it is okay. Yeah, let me just check it. Yeah, the first one is not right. Yeah, because I forgot to turn this uppercase to lowercase. Yeah, even I checked, it is uppercase characters because this is alphabet num. It's this L num. Yeah, I still need to plus c dot lower. Even it is a lowercase, it is still okay. Even it is a numbers, it will still return these numbers. So for this c dot lower, it has no influence to the numbers. Even it is a number 1, and c dot lower is still the character number 1. Yeah. Now let me run it. It should work. Yeah, as you can see, it works. Now let me submit it. Yeah, as you can see in Python, you can check the string equal directly like this. Yeah, even it is on time, but you can directly check it. It's gonna be much faster. Yeah, now let's go to the last problems in single number. So this gonna be a bit mask problem. You can also use try to use other ways, but for me, I think the bit mask is the easiest way to understand and to solve it. So let me prepare a result as 0. So for n in nums, so the result would be XOR with this n. Finally, we just need to return this result because we just need to find the single numbers. So if, for example, those twos are the same, so 2 XOR 2 would still be 0. 0 XOR 1, it would be 1. So this is why. Now let me submit it. And the time complexity is just ON. As you can see, it works and pretty fast. Thank you for watching, and this is for today. If you think this is helpful, please like and subscribe. I will prepare some videos like this. I hope it should be helpful for you to solve Leetcode problems. See you next time.